All right, hello everyone. Welcome back to PC301 workshop, and we are ready with the fourth session of the day. And we have with us Professor Neeldhara Misra from Indian Institute of Technology, Gandhinagar. And this is the second talk on computational social choice, and she'll be talking on using structured ILPs to solve high multiplicity problems. So thank you for joining us once again, Neil. Over to you now.
Okay, great. Thanks a lot, Pratibha. And yeah, so today's talk, as promised, will be in a slightly different setup or a slightly different context of problems. So in yesterday's session, we kind of explored a few examples, or actually we end up talking about just this one problem, which was the lobbying problem in the context of voting. And today I want to just breach another like fairly broad vertical in computational social choice, which is problems related to fair division of resources. Now, fair division is, again, there's of course a lot going on. And again, it's one of those things where much has been said. So I'm just going to focus again on a specific running example. And in fact, I will not be spending too much time on the broader background. In fact, I was just mentioning earlier that Rohit is around, so it's an excellent 5-lecture series, I think, which is like a really nice crash course into like the overall a landscape of fair division, especially in the computational context. For instance, there, I think about half the discussion is focused on the so-called cake cutting setting, which is probably something that you have even heard about in popular culture. And that's the setting where we are looking at the so-called indivisible resources, which may model applications where you're trying to, let's say, divide a piece of land or something like this. So typically that's modeled as I guess you could say the real interval between 0 and 1 without loss of generality. And, that's not the setting that we'll be talking about today. So we'll be talking about the so-called indivisible resources, which are just items that cannot be, the atomic objects cannot be cut up further. And you just want to figure out how to divide them fairly. So with that, with the disclaimers in place. So okay, let's get down. I think I'm done with the disclaimers. So let's get down to the setting of the problem that we will be looking at. So they're going to be n agents, which I'm going to denote by these people here. And there are some items that we're going to want to divide between them. So in the typical setting, and this is where I think sort of the high multiplicity phrase in the title kicks in a typical setting, you have m items, and you're just trying to you're just worried about m items. But here instead, I have m item types, and for each type, there could be multiple items or resources of that type. Okay, and again, as you can imagine, this is obviously sort of a toy picture, but this stuff has serious applications. Okay, these resources abstractly could be anything. They could be distributing, let's say, bands in some 5G spectrum. It could be it could be items that you're trying to settle in a divorce settlement, and everything in between. So all kinds of situations are captured by this problem. So in any case, let's just keep in mind that the literal number of items could be much larger than m. Okay. The next natural thing we want to talk about are valuations. So again, here the valuations are essentially the extent to which every agent likes every item. So this is typically a utility matrix. I have an emoji matrix here indicating the feelings that the agents have for these different items. So Shmita, can you confirm that you can see all of this? Because this is the slide I spent the most time on.
Yes, I can see.
Okay. All right. So yeah, so of course, in like actually working on a problem like this, the evaluations are going to be some sort of numbers. But again, we might be interested in the setting where the number of different numbers that we have are small. And in fact, even for more classical problems, like let's say knapsack and subset sum that involve numbers, the number of distinct numbers that you're dealing with is considered a natural parameter, and there is some work on that to that effect. So that's one of the parameters that we may be interested in. When you look at the utility matrix, you don't see too many different numbers. I will draw your attention to the negative numbers here. Sometimes we like to assume that all utilities are positive, which is to say that the items are such that nobody minds getting it, or is at least neutral. You may have a zero utility like you see to the far right of this matrix. But sometimes you may have a situation where there are negative utilities indicating that somebody actively does not want a particular item. And I think there is a, a problem which is typically called chores, when I think, again, I'm happy to be corrected if I'm wrong, but I think that setting, essentially all the utilities are negative. So all the items are, let's say you're literally trying to divide up, like a bunch of roommates trying to divide up the chores in the house. So nobody really likes any of it. But again, you want to do it in a way that sort of is reasonable for everyone. And we're going to spend like the next few minutes talking about what it means for a division to be reasonable. But so far we have, so this is, I guess, what you would call a mixed utility matrix. You have both positive and negative utilities in the same valuation matrix. So what are we really interested in? The heart of the problem is the problem of finding an allocation. So you're trying to distribute the items that you have among the agents who are around. And again, you could do this, of course, in multiple ways. I mean, if you look at the search space, is of course huge. It's exponential. The many different ways in which you can perform these allocations. But let's just bring back the okay. So this is just some notation that you will typically find, and this is again slightly unusual because you're looking at this high multiplicity setting. So I only tell you how many items of each type are given to agent AJ. Okay. Okay, Pallavi, the utility is, I think, typically the utilities, okay, I guess you could restrict yourself to integer utilities. A very commonly studied special case is when you have 0, 1 utilities. These are called sometimes binary utilities, although that term is used in a different way as well. But I think utilities are typically just rational numbers, I think. So this does you notice that the value that you have for something does not have anything to do with the way you divide something. So we're going to come to what it means to divide, which is what we have here. So this is the allocation. And typically so if the allocation had fractions, then we would call that a fractional allocation. And I think that is, I believe, also something that people look at. I guess there is some notion of sharing, right? So you might say that between two agents, they share an item. This could either be time sharing, or you just violate the axioms and you literally divide an indivisible item. So depending on the application, you might want to allow for that. But for our purposes, we'll just assume that the allocation is a straight up like a nice integral division. So every item either is completely given to somebody or is not given to that person at all, right? So the fractions in the utility matrix and fractions, potential fractions in an allocation vector are different. Okay, so yeah, I don't think I'm going to get too notational throughout, but just for the record, pi sub L sub AJ is the number of things of type L that you give to agent J, and you define this for each agent AJ, you define this for every item type. If you just had items, then typically this would just be a 0, 1 vector, which would just tell you whether the item is given to this person or not. And of course, for a vector to be valid, you want to make sure that the sum of pi L AJ over all agents AJ is equal to the total number of items that are available of type L. Okay, otherwise this allocation is not feasible. Well, okay, is at least less than or equal to is what we want to say. It's possible technically that so there's nothing in the definition that prevents you from not allocating any item at all, but we will see why that may not be so reasonable. Or that, well, okay, again, it's not entirely clear. If you do have negative utilities, you may be better off not giving away some items at all. And then it may be a requirement in your problem wherein you say, oh, we really need to assign everything. So such allocations are called complete. But I think I'm jumping ahead a bit. Let's just talk about, let's just spend some time getting used to the idea of allocations. This is a very natural thing that you want to evaluate in the context of an allocation, which is to say, what is the utility that every agent derives from an allocation? Right. So Sushmita is asking, we can have unallocated items. So a priori, yes, I think the definition of an allocation. So again, maybe I should have written this out explicitly. So for an allocation to be feasible, all you need is that you don't allocate more than what you have. So for instance, here I have 7 gift boxes, and in the allocation also overall I've distributed 7. I cannot distribute 8 of them because I just don't have that many, but it's possible that I just withhold a couple of them. That would still be a feasible allocation. I think an allocation where there are no unallocated items is called a complete allocation, and I think you need to ask for it explicitly. Although in some papers, the only kind of allocations, like so, they incorporate completeness into the definition of the allocation. It's just one thing to quickly sanity check in the beginning, like what does an allocation mean? So good point. So right. So one thing that great. So one thing that I think is something that you'd be immediately interested, given an allocation, is how much do the agents like it, which is kind of given by the utilities that they derive from the allocation. So every agent looks at the items that they have received, and they basically add up the utilities that they have for those items, right? So I may have gotten my additions wrong, but let's just say like this is the sort of thing that happens for this example. In fact, let me bring back the valuation matrix. Maybe some of you can verify if this was correctly done. But also I want to pause at this point to ask, like, what's something that bothers you about this allocation? Like, is there something that you think is not quite right about it?
So the big rectangle on the right with 5, 4, 2, 5, 3, so that tells us how many items each of these people have obtained. Like the first person gets 5, then 4.
Right. Well, I mean, very close. It's not the number of things, but it's how much they value those things that's getting added up. So, for example, if I look at the leftmost agent, she has 3 gift boxes and one of these toolboxes. So she values each of the gift boxes at 2 units, and she values the toolbox at -1. For some reason, she really doesn't like it. So it's 2 times 3 minus 1, which is 5. So that's how we calculate the numbers at the bottom. Good point. I should have been more explicit. Thanks.
So someone got completely 0 values, the
Yeah,
last one.
right, exactly.
So that's not a fair allocation.
Right. So there's already a comment in the chat saying it's not Pareto optimum, and Pratibha has also pointed out that it seems a bit sad that somebody has like a 0 utility. It could have been worse, by the way. We could have. I think you can come up with allocations that are worse than this for sure, in the sense that like you could. Again, what does it mean to say that it's worse? Let's just say that some agents are even unhappier than they are in the current allocation. Right, and I think, yeah, thanks, Rohit, for reminding me to make that explicit. The valuations, yeah, so I guess if you wanted to be super general, the utility, the valuations could actually map, I mean, it could be a map from the space of all possible subsets of items to numbers, right? Because for every possible subset of things that I give you, you tell me how much do you value that thing, value that particular combination of items being given to you. And notice that if I were to actually ask you for your valuations in this very general setting, then it's going to be pretty expensive for me to even note down what your valuation is, because you're telling me how much you value every subset of item types. So let's just assume that you value 2 things of the same type in the same way, just to keep things simple. And to make things even simpler, I'm going to say that I just make note of your base valuations, how much you like every individual item type. And now if I have the so-called bundle, right, this is what usually subsets of items are called. So if an agent is considering how much they value a bundle, the values, we assume that these valuations are additive, as Rohit is pointing out. So you just add up the values for the individual items, and that's how you recover the value for that bundle. This is not the only way of doing things. As I said, you could ask for a more explicit, like for every bundle, you could ask the agent to specify a valuation, which may not be the sum of the individual items. But that's a super general setting where, as I said, even writing down the input is like tricky business. So we will not be talking about that here.
But Neil,
Yeah.
could you represent these objects and their valuation as a vector and then take dot product? For example, this first girl, her valuation of, there are like, it's a 3-coordinate vector, because there are 3 types of objects. So the first item she evaluates as 2. So however number of things that she is given, it's going to be 2 multiplied by that. Then the second object is, so can't we just represent their valuation function as like a vector? And then depending on the allocation, you're just going to do dot product to obtain the valuation of each and every individual. Can't we do it that way?
Yeah, you're absolutely right. So in fact, you look at the valuation, that's the column vector here. So for every agent, you get the column vector for values. And if you go back to this allocation vector, and I just pull out, let's say, the first 3 entries from this pi wala vector, and I take the dot product, then I do get the total utility that that person has for their bundle. That's correct. But notice that in the dot product, what you're doing is that you are in fact taking the sum, right? You are taking the sum of the values that they have for the base items. So I think just following up on what Rohit was pointing out, somebody could say that if you give me 1 gift box and 1 parcel wala box, my valuation for it is not 4, but rather it is 3, because somehow when I get them together, I'm not as happy as when I get them individually somehow. So you could say that, but then to be able to describe that, you would actually have to give me a number, not just so in the valuation matrix, the number of rows that I have will increase. And in this example, for instance, it will become 8, assuming further that, when I take copies of the same item type, they add up correctly. Otherwise, it's even worse. If there are, let's say, 100 items of these 3 types, my valuation matrix will have like 2 to the 100 rows indicating for every subset a separate utility. And that's quite expressively quite expensive. And it's a very general setting, and most of the results that at least I think I'm going to talk about do assume this sort of additive behavior, because otherwise things could be really wild and they become a little hard to argue. Yeah.
Thank you.
Cool. So yeah, but what you said about the dot product is exactly how you would do it, assuming that the valuations are additive, I guess. Yeah, sure. So, right. So I think it's already been pointed out that this allocation is not Pareto optimum. So maybe let's just talk about what that means. And so I think the example that I had here is that if you shift, so maybe let me just show you that again. If you shifted the, what is this, a toolbox or a briefcase or whatever, from the, from the 6th column to the 5th column, then the utilities for both the agents in question would actually improve, because in the 6th column, the utility for that briefcase was -2. So there's a gain there. And the chap next to him actually values the toolbox at 4. So there is a gain there as well. So in this situation, we were able to modify the allocation that we had so that it became one where actually for everyone else it's the same, but for these 2 specific agents in question, they're strictly happier than they are before. So that's exactly what's called Pareto dominance. So let's say we're looking at 2 options, so 2 possible allocations. There's one at the bottom, there's one at the top. I'm sorry that one of them is upside down, but okay. So we're looking at 2 allocations. And we basically ask every agent if so, starting from the allocation at the top, we ask them to compare the allocation at the top with the one at the bottom. And we ask each one of them if they are worse off than before, right? So if everyone is at least as happy as they were before, obviously there's a bit of a glitch. I also have the utilities appearing as this box moved around. Sorry about that. But okay, it turns out that in this example, if you ask each person what was their utility before and after, their utilities are either the same or they get strictly better. And if this is the case, then the new allocation is set to Pareto dominate the old one. Okay, so is this definition clear? Can you maybe give me a +1 in the chat if it makes sense when one allocation dominates another one? Okay, awesome. All right. So Pareto efficiency simply means finding an allocation that cannot be Pareto dominated. And it's should be clear that Pareto efficient allocations exist because the space of allocations is finite, and you start with one, and if it's, at least in principle, you start with an allocation, and if it's not Pareto efficient, then there is one that Pareto dominates it, so you kind of move to that one, and you keep doing this till you get stuck, right? So I think Pareto efficiency handles the kind of issues that we have with some of the, like the arbitrary allocation that I showed you, and you said, well, this is not so nice because you could move things around and people would be happier. But is okay, so it's a nice concept, but let's consider this example. So here is an allocation where you give everything to one agent, and everybody else gets nothing. Well, they get an empty trash can, but that's just denoting the fact that they don't get anything. Right, so Shmita, there isn't an unlimited supply of every object type. So this was, the pool is essentially, in this example, you have 8 objects of the first type, 7 of the second, and 5 of the third. And typically that's exactly what your input to the problem is. It's M1, M2, M3, up to M sub n, where M sub I tells you how many objects are there of type I. Right, so it's not unlimited. So yeah, the question here is this a Pareto efficient allocation?
Yes.
Right. It is a Pareto efficient allocation, and the reason for that is that the person who's gotten everything does have a strictly positive utility for all the items that he has. So in any other allocation that's different from this one, I mean, notice that every item has been allocated, and it's been allocated to this one person. So if you had to move away to a distinct allocation, then, well, I mean, you would have to take something away from this guy, because if you don't, then you naturally wind up at the same place because you don't have anything left to give to the other people. So for moving to a different allocation that's feasible, you have to take something away from this chap, and he's not going to be happy about that. So even if everyone else is in the same state as before or strictly happier, you're definitely going to make this person strictly less happy. So this is in fact, so it's not possible to Pareto dominate this allocation, right? But would you call this a nice allocation? Is this a reasonable allocation? And can we articulate why we feel that it's not reasonable, right? What is it that we want to, so in the previous example, I showed you an allocation from where which sort of motivated us to define Pareto efficiency. And now is there something that you see here that motivates you to come up with maybe a different definition of something that you would also like to have? Yeah, we want to reduce the number of people who are feeling left out. Sanjukta is saying it's not proportional. That's a good point. If we just calculated the utilities, and I think the reasonable thing to say is that you want every person's utility to be, let's say there are n agents, then, or let's say for instance, as is the case here, I think there are 8 agents. So if you look at the utility that every person derives from an allocation, I guess it's reasonable to say that they would feel happy if they got at least 1/8 of the total utility that they have for all items for the entire pool, right? Yeah, can we reduce, right? So there is an issue of envy, and Pratibha is saying, can we reduce the number of people for whom we can find a better allocation? Yeah, so there are these people who are, yeah, that's a good point. So you could look at the set of people who are feeling left out for whatever notion of left out, and you could ask if you could move to an allocation where that number reduces. Okay, so essentially, one way of looking at this situation is that everyone is kind of upset, and they're upset because somebody has gotten a really good deal, and relatively speaking, they have a raw deal. So that motivates us to define this notion of envy-freeness. And so envy is a concept which is motivated by this idea of people looking over their shoulders and evaluating each other's bundles for their own satisfaction. So yeah, I mean, philosophically, and like maybe you don't want to bring this into play, but practically, I think it's a very natural notion. So let's say we look at X, and so X and Y have these bundles allocated to them in some hypothetical allocation. And let's look at how X perceives or views Y's bundle. So she's going to look at Y's bundle, but evaluate it according to her her valuation function. Okay, so she's not concerned about what Y thinks of his own bundle. So Y may be either very depressed or neutral or super happy with his bundle. That's not what X is worried about right now. So X has her own bundle and she's going to evaluate Y's bundle relative to her own. So again, assuming that I got the addition right, there's a good chance that that's not the case, but let's just say that when X evaluates Y's bundle, then she gets a total value of 14. And Y does the same. He evaluates X's bundle using his valuation vector, and he gets a valuation of 12 for X's bundle. And X is going to compare this with her valuation of her own bundle, and that's going to be the same for Y. Okay, so it turns out that in this example, both X and Y are kind of not insecure about what they have relative to each other, right? So when X looks at her own bundle, she's like, okay, I have something that I value at 15, and this guy has something that I value at 14, right? So I wouldn't exchange, right? Y has a similar worldview, so he has something that he likes at 14, and he doesn't like the other bundle more than his own. So this is a situation where you would say that there is no envy, and you can easily come up with examples where this is not the case, and one agent may feel that somebody has a better bundle than their own, okay? And there are, of course, various other notions that kind of capture, like just coming back from here, as I think as Sanjukta was already mentioning, you could also talk about proportionality. You could also talk about the so-called equitable allocations, which is kind of a related concept where you want everybody to get the same value according to their own valuation. So, but I won't be getting into those alternate definitions for now. We'll just say that this is the sort of thing that makes for a happy situation in our case. This is a fairly fundamental, very well studied sort of notion. This is what we're going to stick to. Now, it turns out that even if there are just two agents, actually, even before going into the computational aspects of figuring out, so the computational question that we will be interested in is given the input, which is all of these agents and their utility matrix with respect to these item types, we want to know if there exists an allocation that is both envy-free and Pareto efficient. Notice that both of these notions are it makes sense to use them in tandem, because you can imagine that there are Pareto efficient allocations that don't make sense at all. We have seen an example of that. And you could also think of envy-free allocations, which are kind of trivial to come up with. So if you don't impose the Pareto efficiency, if you don't demand for it, then you could trivially solve the question of whether there is an envy-free allocation. Can somebody tell me what's the sort of a trivial allocation that's envy-free? It kind of goes back to Sushmita's earlier question about should every item be allocated? So if the answer to that is no, I don't care about every item being allocated, then what's a trivial envy-free allocation? It's to not allocate anything, as Sanjukta has already pointed out. So if you don't give anybody anything, then there is no envy, right? A weaker thing would be to say, okay, I'm not happy with that, so at least give me a complete allocation, right? So give me something that allocates every item, and then already things start to look a bit more non-trivial, a bit more interesting. So I think before moving on, I should also point out that there are issues of existence. So having set up everything, the question of whether an envy-free and Pareto efficient allocation exists is a fair question. And or even an envy-free and complete allocation, does it exist? And again, there are very easy examples where you can see that you might be in a situation where the allocation that you're looking for doesn't even exist. And this is again a pretty popular situation, so or a well-known situation. So maybe somebody wants to point it out in the chat. What's a situation where a complete and envy-free allocation does not exist? It's like every Bollywood love triangle ever.
Yeah, if there is a limited resource which is like preferred by two parties, yeah, exactly. We have in chat,
Yeah.
and you have only one of that item.
Right, yeah. Yeah, just after I said a love triangle and you said limited resources, pretty amusing. But okay, so yeah, sure. If you have just one item that's contended for by two people, and let's say they both value it non-trivially, then there is no way that again, this is with the assumption that we take the indivisible part seriously. This one item has to be wholly allocated to one of the two agents. So even in a simple situation like that, you don't necessarily we are unable to achieve both completeness and envy-freeness. So that motivates this whole line of work about relaxing envy-freeness as a criteria, and we'll talk about that on the next slide. But before getting there, let me just say that even in very special cases, so I'm just going to call these EEF allocations for short, efficient envy-free allocations. So I think the most general problem of finding EAF allocations, I think, is even sigma 2 complete, if I remember that right. Again, please feel free to correct me if I'm wrong. But even in special cases, like when there are two agents, or even when there are these 0, 1 utility matrices, even then this problem, it turns out to be NP hard. So for two agents, this should probably look like a familiar problem that you have seen. So any guesses for why it's hard even when there are just two agents? And okay, Saket, I just paused to ask why would the problem be NP hard if there are only two agents? Yeah. Now that's a good point. Maybe others didn't hear that paused in the context of this question, but okay. All right, I'm just going to put that out there and move along. As I said, the fact that these allocations may not even exist, and the fact that they're often hard to find, even in very restricted circumstances, has motivated a very substantial line of research on relaxed concepts of envy-freeness. So one thing that I don't even have on the slide just came up in the discussion, which is what if there are what if you allow for fractional allocations? So what if you allow people to share? And that already starts to, at least a little bit, it starts to take care of this one item and two contenders kind of a situation. Maybe if it was maybe it was some sort of an object that maybe people could keep, they could time share it, maybe like a house or something. Maybe you could, yeah, have a time sharing a solution. So in general, you want to come up with solutions that minimize the number of sharings, because that's not ideal. So that's one way in which people have looked at trying to relax the criteria of envy-freeness. But I think, yeah, a very popular concept is envy-freeness up to one good, or EF1, which is a situation where you say, okay, let's again go back here, and it's again people looking at each other's bundles, but they say, okay, I'm not going to be I'm not going to be so petty about this, so let's just remove let me just remove one good from your bundle. Like, I'm not taking it away from you in the allocation, all right? So in the allocation, you still have exactly what you got. But as a thought experiment, when I'm comparing my bundle with yours, I set aside one item, and then I ask myself if I still envy your bundle, okay? So in some sense, without loss of generality, you could set aside the item that you value the most, and you say, okay, I'm just going to I'm just going to ignore this, not look at it, and then I look at the rest of your bundle and then make that comparison. And of course, this is mutual. This is how you determine envy. And again, this takes care of this one item, two people sort of a situation, because once you eliminate one item, there's nothing left to compare. There is a stronger notion called, okay, sorry that I just have to keep playing that multiple times. A stronger notion called ENVY-FREENESS after any good. In the previous notion, we said you could remove anything, and in particular, therefore, without loss of generality, you remove the most expensive thing from the other person's bundle. But ENVY-FREENESS after any good means that no matter which good you set aside from the other person's bundle, you should still not experience envy. So in particular, even if you remove the item that you like the least, even then you should not experience envy. So I think this is, so I guess if you have an allocation which is EFX, it's EF1, but not necessarily the other way around. So I always get these things mixed up. So if I did, then please correct me. But okay, so these are two fairly popular notions. And for EF1, I think for EFX, a bunch of things are still open with some recent advances. For like, I think it was open even for 3 agents, and I think that, but I could be getting that mixed up. But for EF1, I think the situation with respect to both existence and thank you, open for 4 agents and additive valuations. And right, EFX does exist for 3 agents, and I hope I was not mistaken when I said that that was a relatively recent development, but okay. All right, so EF1 again, papers by members of the audience here, I think shows that you can get Pareto optimal and EF1 I think for general matrices in pseudo polynomial time, and for and in particular, of course, for 0-1 valuations, that becomes polynomial time. And I think whether the pseudo polynomial can be improved, pseudo polynomial because the utilities could be are represented in binary. So I think it's polynomial under the assumption of unary representations, and I believe it's still open to figure out if you can get EF1 and PO, right, in truly polynomial time, I guess. So again, would appreciate a confirmation in case I got that mixed up. There's also a whole line of work on reducing envy with money. So can you introduce some money in the system, and again, what's the least amount of money that you need to introduce to kill the envy that people may be experiencing? Again, this is just following up from EEF and getting things to be better. There's also a notion of graph ENVY-FREENESS, which may be of special interest to people who like working with graphs. So I think both settings have been explored, but the natural one that I mean when I say that you want to relax this fairness concept of EF is to say that you have a graph on the set of agents to whom you want to allocate these resources, and you say that you experience envy only among people that you know. So think of this graph as being some sort of a social network, and the envy being constrained by visibility in this network. So I only envy people that I see or people that I know. And again, so in this context, it's probably a lot of it depends on the structure of the graph and so on. And I think people have started looking at this quite a bit. So I think there are at least a few papers in the recent past that explores. So I think it's called ENVY-FREENESS Respecting Social Networks, and is at least the title of one of the papers that I can remember. And this is something that has also been looked at in the cake cutting setting quite a bit. The other kind of graphs that comes in the context of fair division problems is when you have a graph imposed on the items, which may make sense if the items actually represent some sort of geographic entity, and you want pieces, you want collections that are somehow connected. So again, so this is, I guess it's called connected ENVY-FREENESS, and you want, connected fair division problems. And again, here I don't know if there are I don't know if there are any works that look at both situations combined, but independently in connected pair division problems, you want each piece in the allocation to induce a connected subgraph of the graph that you have on the items. So those are. I don't know if I would like to propose that as per se being a relaxation of NV-freeness, because in fact, once you start imposing these connectivity requirements, um, then actually things may become harder, and you may in fact start getting more non-existence. And there are some computational intractability results, even when like situations where even when the graph is a path or a star or something super simple like that. But yeah, nonetheless, it hasn't. Yeah, I mean, you could still look at some fairly interesting parameters, and I think there are some papers to that effect, but not a whole lot. Um, and sorry, I missed that question. A graph on items is what we were just talking about. So hopefully that was addressed sort of naturally. But yeah, that's right. I mean, there, as I said, usually the constraint, like once you impose the graph on items, usually the constraint is connected bundles. I don't know if there's any other sort of setting that people explore after imposing the graph on items. Um, Right, I think Sanjukta's question was addressed by Rohit in the chat, so just let me know. Yeah, EF1 is if you can remove something, right? And EFX is no matter what you remove, you still don't have NV. Okay, so this is just a snapshot from one of these papers that specifically explores this high multiplicity setting from a parameterized perspective. And again, three natural parameters that emerge is the number of distinct numbers, the number of items. Here, by the number of items, we really mean the number of item types, and the number of agents. So it turns out that you get a lot of hardness when you just look at the number of agents. So it makes sense, except for the case of additive 0-1 utilities, which is something that we will sort of look at just a bit. So I think it makes sense to ask if the number of agents plus something makes sense, because already for additive and identical, you get W hardness and so on and so forth. So I won't get into the para-NP hardness for binary preferences, because I think the notion of binary is a little bit different from just saying 0-1 preferences. And given the kind of time we have, I don't want to get into that right now. What is unary preferences? It's just unary representation. Let me just, sorry, what I said I don't want to get into is the dichotomous preferences, because it's easy to confuse dichotomous and 0-1. Sorry, the unary versus binary is just the representation. So binary is succinct representation, is additive is when the representation of the utilities in the utility matrix. So unary is when those numbers are given to you in unary. That's the distinction that we're making here. Okay, so all right, great. So in these, so again, it's going to be an ILP approach. So I'll talk about the parameterization by the number of agents for additive 0-1, which is pretty much the same as saying n plus z, because the number of different numbers is just a constant in that setting. It also works for identical. Interestingly, what was open is what happens when you just have additive valuations. Even if they're represented in unary, right? It wasn't clear. So we'll just look at this ILP approach, and we will see why it's not clear how you make it work for additive preferences. I'll just mention a development from EC19 where this was resolved, and I think there's some more recent work where it now works even without this assumption of unary representations, which is quite interesting. And okay, sure. I think I was asking about two agents earlier, Herschel. So if you have a comment, please feel free.
Yeah, I'm sorry, but I was just wondering if we could if partition could be thought of as a special case, because if let's say every item was only available once, like there are no multiple copies available for each item, and if there are only two agents who identically value all the set of items, then can we just say that for the allocation to be complete and be free as well as Pareto-efficient, we would have to necessarily distribute them evenly.
Yes, I think you would be quite right about that. Yes, thanks, Arshil. So yeah, I think the point being made was that the NP completeness for the special case of two agents comes from the fact that this problem captures partitions. So the only way to ensure a complete and exactly NV-free allocation between two agents is if so just make sure that the two agents have the exact same valuations, and those valuations correspond to the numbers of the partition instance. So that exactly works. So yeah, thanks for pointing that out and figuring it out. Okay, so just to use the terminology from this paper, we call this vector, which represents the utilities for a particular item type. It's fingerprint, and notice that you could have like 1,000 of these items, but all the agents value each one of these in the same way. So these are indistinguishable, and we want to really take advantage of that. So if Z was the number of different, so the reason I have like the emoji version up here is because hopefully it conveys the intuition that the number of different things in this matrix is bounded. So let's say that the number of different numbers that you see in the utility matrix is Z, then how many different fingerprints can we have? That I'm just asking how many ways can you form these, how many vectors are there of dimension m over Z distinct values? Exactly, Z to the n. Sorry, yeah. So n is the number of agents. So Z to the n. That's the number of distinct fingerprints that we have. So essentially, this is so the number of item types really that we care about is bounded by Z to the n, and the reason for this is so let's I mean, I guess I want to make the simple point that if you exchange two items of the same type, then it doesn't make any difference in the allocation. Okay, so I should have, okay, I think I had a bunch of skipped. Okay, so let me just say that this is in general. I think it's okay. So let me just talk about exchanges as a general concept. You could morph one allocation to another one by just talking about the difference in the number of items. You could just talk about how much each person's bundle changed, right? And um, you can actually, okay, so again, this is a very special kind of exchange where you're just exchanging two items of the same type. So even though these were physically two different items, notice that nothing really changed in the allocation. So if the previous allocation was EEF, the new allocation will also be EEF because the utilities, everything is exactly the same. So this is what we want to take advantage of, with the fact that the number of different item types is bounded. So but I also, okay, so I'll come back to why I wanted to talk about exchanges in general. When we talk about trying to capture Pareto dominance, I'll probably make a mention of that. But first, let's think of how we can capture writing an NV-freeness constraint as, as an ILP constraint. So again, I want to introduce variables. The so the variable XIF denotes the number of items of type F. So remember that this type F ranges from 1 to m, but we just argued that m is bounded by Z to the n because you don't like if the number of numbers and number of agents are bounded. This is bounded as well. So if we use these variables to denote the number of items of type F allocated to agent I, and let's just recall that which is F, which is an item type. This was what we called a fingerprint. So Fi, the ith coordinate. So this is a vector with n coordinates, one coordinate per agent, and f of I is the ith entry, which means f of I denotes how much agent I likes an item of type F. Okay. So if you want to model NV-freeness as an ILP constraint, how would we do it as a combination of these variables? So remember that, so we would have to say something like for every pair of agents, I and I prime, we want to describe using these variables how much, so remember that the variables X actually describe completely the allocation, and we want to use Xi's in conjunction with F's to describe the utility that the agent I derives for their bundle. So how would we do that? I think it's pretty natural. So I'm hoping somebody will point it out. Okay, I'm sorry. Maybe this is also like a pain to type out in the chat. So I was hoping somebody would just speak it out loud. But okay, so hopefully, so for every agent, okay, sorry, I think this should have been like a I prime. I don't know. I forgot to type that out. But okay, so for every pair of agents, I and I prime, I think let's just focus on the sum because I think then the constraint is kind of easy. So for every agent I, we just sum how much did they get for each item type. And for each of those, that gets kind of boosted by f of I, which is how much they value that item. That's it. That's all that's going on here. And so this on the left, you see how much agent I values sort of their bundle. And on the right should have been how much agent I prime values their bundle. Okay, so, and this is a constraint that you throw in for every pair of agents I and I prime. Okay. So these are ENVY-FREENESS constraints. You're going to if you come up with if you solve your ILP and you get numbers for the exercise and all of these constraints are satisfied, then you are in business. You have ENVY-free allocations, but they may or may not be Pareto efficient. They may or may not be complete. So we want to kind of encode that. But Pareto efficiency doesn't seem okay. So how would you encode Pareto efficiency using these constraints? I mean, using linear constraints, using these variables, and using the F vectors. So, okay, I'm not sure, but hopefully it's fair to say that it's not obvious for whatever it's worth. But it turns out that if you have preferences which are 0, 1, or if you have preferences that are additive and identical, then it turns out that Pareto efficiency can be captured by two simpler things, which is completeness and non-wastefulness. So if you make sure that everything is allocated and everything is allocated in a way that, by the way, I think let's just assume for simplicity here that this is not a mixed utility matrix. Everything is positive. Strictly positive or 0, so essentially non-negative. Anyway, so essentially, if every resource is given to somebody who values it non-trivially, and you actually allocate everything, then you do have then you do get Pareto efficiency. But this is in the special case of identical or 0-1 preferences, and that's why those are the cases that work out nicely here for the ILP setting. So this is yeah, so additive identical binary is more general than additive identical unary. So so I think all of that works out because of the fact that Pareto efficiency is captured in this way. So again, sorry, I have a skipped slide here. I don't want to. Okay, so here, let me just say that writing down completeness and non-wastefulness constraints using ILP is a fairly straightforward exercise. So I had that slide, but I kind of folded it out because it's completely it's probably like a cute exercise, but it's easy to write that out. It is a lot more non-trivial to figure out Pareto efficiency in the general case, and that's where I think this notion of exchanges turns out to be useful. So a key thing so this is moving on to the results in the EC19 paper. So they define these notions of exchanges. Again, I don't think this is particularly important here, the notation, but the key thing about capturing Pareto efficiency is that if you have, in some sense, if you have an allocation that gets Pareto dominated by another allocation, then you can find a Pareto dominating allocation somewhere close by. So that gets captured by this idea of exchanges where, so the difference between the original allocation and the dominating allocation, in some sense, the change which is described by the amount by which the number of items in each agent's bundle changes from the old to the new allocation, that change can be bounded as a function of the maximum utility that you see in the utility matrix. So that's sort of an interesting, combinatorial observation, and they leverage that in a very interesting way to be able to write down ILP that sort of captures the problem. In particular, they use what are called combinatorial n-fold ILPs, which are, again, I think the best way to get a sense of this is to actually take a look at the paper. I don't think I'm going to do this any justice at this point, but it turns out that these are ILPs where the constraint matrix has the special structure. So you have a submatrix D. I think this is called some bifold product of D and A or something like this. Again, I don't remember the exact matrix terms, but the idea is that D is a small matrix, and D and A are small matrices, and the constraint matrix has this particular shape. And I think from the FPT point of view, what's interesting is that it's FPT in the values of the matrix and the dimensions of the submatrix D. But the submatrix A repeats n times, so that's like this n by n block that you see here. And the n does not feature in the exponential blow up. It's like a n cubed times some f of the dimension of D sort of a running time that you get. So it turns out that the Pareto efficiency constraints can be captured using a combinatorial n-fold ILP, roughly speaking. Again, not getting into the details of how exactly it is done, but not only that, so with this, I think what we got was FPT algorithm for the case when the utilities were represented in unary, but it turns out that using something called parametric ILPs, again, I'm not going to get into the explicit definition here, but you can even get rid of this constraint that the utility should be specified in unary. So hopefully I'll upload a version of the slides where there are links to all of these references. And in the upcoming AMAs, there's a follow-up on the EC19 paper, which talks about how, I mean, I don't think it's an exact implementation of these same family of ILPs there, but with suitable modifications, it turns out that these algorithms can actually be made very practical, and they get like fairly interesting results on at least the splitted data set, if I remember this correctly. So that's those are, I think, two pretty interesting developments from where we started. So yeah, I think it turns out that this combinatorial ILP allows for pretty general theorems. Although I stated it for EEF, it turns out that the theorem in the paper is quite a bit more general, and it gives you this FPT result, FPT in n plus U max, the maximum utility, which is a little bit different from the other parameter that we saw, which is the number of distinct utilities. So so you get FPT in n plus U max for fairly general combinations of fairness and efficiency criteria. So you could cook up your own like combination of things and check if it falls into this framework. It also captures all of this, like, so you can imagine that the ENVY-FREENESS constraint we wrote can be easily adapted to account for things like graph ENVY-FREENESS and other variations of ENVY-FREENESS. So so it's a pretty powerful and general framework. So I think the first takeaway is, like, if you have a question and in particular you're interested in this choice of parameters, it may be interesting to check if this framework already gives you something. But in terms of questions to explore, I think even though this is a nicer algorithm than it's a nicer running time compared to the standard Lenstra running time, because you take advantage of this. In fact, I think there's a SR 2017 paper which gives numerous applications of combinatorial n-fold ILPs and how you get better running times as a result of exploiting this additional structure in the constraint matrix. So even though the running times are better, I think even after using the hammer, I think there's still a lot of specific questions that are still open in terms of getting better running times compared to what you get from the general machinery and framework. So I think I'll stop with that. I hope I haven't gone terribly over time, but if there are any questions, then this is a good time. Yeah.
Thank you so much for the talk.